Hello Internet, Parag Dhawan here. We are on day 10 of Kaggle's 30-day ML challenge wherein we will study about underfitting and overfitting. At the end of this step, you will understand the concept of underfitting and overfitting and you will be able to apply this idea to make your model more accurate. Experimenting with different models. Now that you have built a reliable way to measure models accuracy, you can experiment with alternative models and so which gives the best prediction. But what alternative do you have for models? You can see scikit-learn documentation that the decision tree model have many options. The more important option determine the tree depth. Recall the first lesson in the course that a tree depth is a measure of how many split it makes before coming to prediction. This is a relatively shallow tree. Does house has more than two bedrooms? Yes, no. Lot size larger than 8,500 square feet? Yes, no. If it is no, predicted price is 1,46,000 or 1,88,000. If lot size is 11,500, if it is no, then predicted price is 1,70,000. If yes, predicted price is 2,33,000. In practice, it's not uncommon for a tree to have 10 splits between the top level and a leaf. As the tree gets deeper, the dataset gets sliced up into leaves with fewer houses. If a tree only had one split, it divides the data into two groups. Each group is a split again. We get four groups of the house. Splitting each of these again would create 8 groups. If we keep doubling the number of groups by adding more split at each level, we will have 2 to the power 10 groups of houses. By the time we get to the 10th level, that has 1024 leaves. When we divide the houses among many leaves, we also have fewer houses in each leaf. Leaves with very few houses will make predictions that are quite close to that home actual value, but they may make very unreliable prediction for new data because each prediction is based on only few houses. This is a phenomenon called as overfitting, where a model matches the training data almost perfectly, but thus poor in validation and other new data. On the flip side, if we make our tree very shallow, it doesn't divide up the houses into very distinct groups. An extreme, if tree divides house into only 2 or 4 groups, still have a wide variety of houses. Resulting prediction may be far off from most houses, even in the training data, and it will be bad in validation too for the same reason. When the model fails to capture important distinction and pattern in the data, so it performs poorly even in the training data, this is called as underfitting. Since we care about accuracy on new data, which we estimate from our validation data, we want to find the sweet spot between underfitting and overfitting. Visually, we would want to low point of the rate validation curve in the figure. Underfitting, overfitting, for the validation curve, we want this lower point. Example, there are few alternatives for controlling tree depth, and many allow for source route through the tree to have greater depth than the other routes. But max leaf node argument provides a very sensible way to control overfitting versus underfitting. The more leaves we allow the model to take, the more we move from underfitting area in the above graph to overfitting area. We can use a utility function to help compare mean absolute error scores for different value of max leaf depth leaf node. For creating that function, we are importing scikit-learn metric mean absolute error. From scikit-learn.tree, we are importing decision tree regression. We are defining getME function which receives max leaf load as argument, train valx, train y, val y as an argument. We create a decision tree model with max leaf node as the argument max leaf node received, and random state as 0. We fit the model on the training data. We predict on the validation features, create a prediction value. We compute mean absolute error on the predicted value and actual values of y, and return the mean absolute error score. So we have written a function which is returning mean absolute error for a number maximum leaf node provided and the training and validation data. The data loads in train x, val x, train y and val y using the code you are already seeing. So in the next cell, click on the cell and run this cell. In the next cell, we are reading the data and calling the function for different size of leaf nodes. So importing pandas as pt, storing the path of CSV file in path variable, reading the CSV file using panda read CSV function and storing it in Melbourne data frame. Then we are removing the null values using drop NA function and creating filtered Melbourne data frame. We are segregating the predictor variable using data frame dot price. We are collecting features as a list and then calling the feature using the data frame to get the features in variable x. Using scikit-learn.model selection, we are importing train test split function, and we are dividing x and y in train x, val x, train y, val y. Random state is equal to 0 to produce the same result if we run the same code on different machine. Click on the cell and run the cell. You have train x, val x, train y, val y. Now you are running a for loop. You are iterating over a tree depth of 50, 5u, 50, 500 and 5000. You are calling get MEA function. You are passing 5u, 50, 500 and 5000 every time, and after running this function you have mean absolute error of each iteration. In the next print statement you are printing the mean absolute error. So this for loop runs over the maximum number of leaf nodes and then get the mean absolute error. Click on the cell and run the cell. You can see mean absolute error for 5 nodes is 34,000, for 50 nodes is 25,000, for 500 node is 24,000, and for 5000 node is 25,000. So you can see that 24,000 is far close to the predicted value, means our prediction is not deviating from the actual value by 24,000. That is so we can use max depth of the tree as 500 to get more accurate result. Conclusion: overfitting, capturing spurious pattern that won't recur in the future, leading to less accurate prediction. Underfitting, failing to capture relevant pattern again, leading to less accurate prediction. We use validation data which isn't used in the model training to measure the candidate model accuracy. That's it for this video. Thanks for watching. Do hit that subscribe button for more such technical content. See you in the next video.